Hello everyone, welcome to the channel. Just a minute, I'm checking once again that live started or not. Just a minute. So this is the third session of Ordinary Differential Equation question practice series for the upcoming CSIR NET and GATE exam. Okay. We already discussed two sessions, and in the two sessions, in first session we already solving 10 questions, and in the second session we already solved 5 questions from CSIR NET previous year, that is 2022 फेब का क्वेश्चन जो था वो क्वेश्चन सॉल्व किया था. ठीक है. So in this session we are discussing also 10 questions, and this session is based on Wronskian. Okay, so Wronskian, this is dedicated on Wronskian. So those who are new in my channel, please like the video, comment if you have any doubt in the comment section below, and don't forget to subscribe the channel. Okay, so let's start with question number 16. Okay, the question 16 says that let y1x and y2x defined on 0 1 be twice continuously differentiable functions satisfying y double dash x plus y dash x plus yx is equal to 0. Let wx be the Wronskian of w1 and w2 and satisfies w half, this is equal to 0. We know the concept that Wronskian of a differential equation is either vanish throughout the interval. Okay, throughout the interval. Suppose the interval is AB. Okay, y1 y2 belongs to AB, w y1 y2 belongs to AB, or this is belongs to AB throughout the interval or never vanish. Okay, never vanish on the interval, suppose AB. Okay, so here it is given that the interval is 0 1. Okay, and w half, that is w at half equal to 0, that means half is a point of the interval 0 1. Okay, that means this is vanish at one point, means this is vanish throughout the interval. Okay, so w half is equal to 0, or any point between 0 and 1 is equal to 0, w at that point is equal to 0, means Wronskian of throughout the interval, Wronskian of x is equal to 0 for all x belongs to closed interval 0 1. Okay, so here first option clearly correct, and remaining answer are obviously the incorrect one. Okay, now go to the question, next question, question number 17. This question says that let y1x and y2x form the complete set of solutions of the differential equation y double dash x minus 2x y dash plus sine of e to the power 2x square into y, this is equal to 0, x belongs to 0 1, and this is the given y1 at 0, this is equal to 0, y1 dash 0, this is equal to 1, y2 0, this is equal to 1, and y2 dash 0, this is equal to 1. Then the Wronskian of the function x. Okay, so at Wronskian at this point. So first we know that Wronskian of the function y1 or y2, this if y1 and y2 are the set of complete solutions, this is equal to y1 y1 dashed and y2 dashed. Okay, so this is at the point x or any arbitrary point. Okay, and this is equal to w at the point x, suppose. Okay, y1x any point, y2x, y2x, and this is x. Okay, now if we put x equal to 0, and since the value of these 4 functions y1 y2 dash y2 and y1 dash, these 4 functions are given at the point 0. So if we put w 0, then this gives y1 0, y1 dashed at 0, y2 at 0, and y2 dashed at 0. Okay, so we put the values. Y1 dash 0 means y1 0 means 0, this is 1, this is 1, this is 1, so this is equal to clearly minus of 1. Okay, now we apply the Abel's formula. Okay, so this Abel's formula means w at x, this is equal to any constant a into exponential minus integration of suppose the differential equation is p y double dash function of x plus or p1 p0 p1 x into y dash x plus p2 y, this is equal to 0. Then this is integration, means this is p1 by p0 into dx. Okay, this is the functions of x, that is coefficient of dy dx by coefficient of d2x dy to minus of integration dx. This is equal to a, this is the Abel's formula. Okay, Abel's formula. This is equal to a e to the power p1 by p2 means minus integration 2x by 1 into dx minus 2x. Okay, this is equal to a e to the power integration 2x dx, that means a into e to the power x square. Okay, now we apply this condition w0 equal to minus 1, so wx this is equal to what, a e to the power x square. Okay, so w0 this is equal to minus 1. To find the value of a, this gives minus 1 equal to a e to the power 0. Okay, so this gives a equal to minus of 1. Okay, so therefore w of x this is equal to minus e to the power x square. Okay, now we have to find the value of Wronskian of x at the point x equal to 1. Okay, so simply we put the value of x equal to 1. So w at 1 this is equal to minus e to the power 1 square, this gives minus of e. Okay, so the correct answer is option B here, minus of e. Now go to the next question. This is question number 18. The question says that let w1 pq let pq be the continuous real valued function defined on minus 1 1 and ui from minus 1 1 to r, I equal to 1 to be the solutions of the ODE d2u dx2 plus px du dx plus qx into u, this is equal to 0, satisfying u1 0 this is equal to 0 and u2 0 this is equal to 0. Let w denote the Wronskian of u1 and u2. Then what, here 4 options are given. Now if we calculate the Wronskian of x, this is equal to u1 x, u1 dash x, u2 x and u2 dash x. Okay, now at the point 0 these two values are given. So if we calculate the value at x equal to 0, then this gives u1 0, u1 dash 0, u2 0 and u2 dash 0. Okay, but the value of u1 dash and u2 dash are not given in the question. Now if we simply put the values of u1 and u2, then we get this is 0 and this is 0, that means u1 dash 0 and u2 dash 0. Therefore whatever the value of u1 dash 0 and u2 dash 0, this is equal to clearly 0. Okay, if since these two conditions are all not given, but although if these two are 0, that means this is completely 0. Okay, so that means w at 0 this is equal to 0, and we know that Wronskian of the functions is vanish throughout the interval, either vanish throughout the interval or never vanish throughout the interval. Now 0 is the point in between minus 1 1 1. Okay, so 0 belongs to clearly minus 1 and 1, which is the interval given in the question. Okay, so at one point of this interval Wronskian equal to 0 means throughout the interval it is 0. Okay, therefore the C option says that Wronskian is 0 for all x belongs to minus 1 and 1. So this is correct option, and we know that if Wronskian equal to 0, then these two solutions are linearly dependent solutions. Okay, therefore C option is correct, and Wronskian 0 non-zero this is incorrect, and Wronskian this is independent, this is also not correct. Therefore B and C options is clearly correct here. Go to the next one. Let px be the continuous function on R and w be the Wronskian of two linearly independent solution of y1 and y2 of the ODE d2y dx2 plus 1 plus x square into dy dx plus px into y, this is equal to 0, and w at 1 equal to a, w at 2 equal to b, and w at 3 equal to c. Now we first find the Wronskian with the help of Abel's formula. Okay, a to the power minus integration, this is the coefficient of dy dx means 1 plus x square by coefficient of d2y dx2 means 1 into dx. Okay, this is equal to a e to the power minus integration of a1 plus x square into dx. Okay, so this is equal to a e to the power minus of x plus x cube by 3. So this is the value of the Wronskian. Okay, now we apply w at 1, this is equal to a, simply a. Okay, so this means we put the a equal to what, a e to the power minus of 1 plus 1 by 3. Okay, this is equal to a e to the power 4 minus of 4 by 3. Okay, that means a by what, e to the power 4 by 3. Okay, the value of a equal to, that means a equal to a by e to the power 4 by 3. Now if we apply w at 2, this is equal to b, this gives b equal to a e to the power minus of 2 plus 8 by 3. This is equal to a e to the power minus 6 plus 14 by 3. So this implies b equal to a by exponential 14 by 3. Okay, this is the value of b. And now since w3, this is equal to c, this implies what, c equal to a by exponential, what is the value, 1 plus 27 by 3. Okay, so this is equal to a by exponential 36 by 3. Okay, so now we find the value of a, b and c, small a, small b and small c. Now we know that since exponential is an increasing function, clearly, therefore e to the power 36 by 3 is clearly greater than exponential 14 by 3 is clearly greater than exponential 4 by 3. Okay, now this implies 1 by exponential 36 by 3, this is less than 1 by exponential 14 by 3, this is less than 1 by exponential 4 by 3. Okay, now here one a is here. Now there are two conditions even occur. If a is positive, okay, then there is no change in the inequality. A by exponential 36 by 3 less than a by e to the power or exponential 14 upon 3 a by exponential 4 by 3. Okay, now if a is negative, that means what is the value of this, this is completely a, b and c. Okay, therefore this means c less than b less than a. Okay, we get one conditions, and if a is negative, then the opposite conditions is occur. That means if a is negative, okay, that means we get also a greater than b greater than c, the similar case. Okay, therefore this is the answer, either a less than b less than c or a greater than b greater than c. Okay, therefore b option is clearly correct here. Now go to the next question. Let wx be the Wronskian of two linearly independent solution of the ODE. This is a very simple question. Okay, 2y double dash plus y dash plus t square y, this is equal to 0. Wronskian means what? By Abel's formula, w of t, this is equal to a e to the power minus integration coefficient of first derivative by coefficient of second derivative into dt here. Okay, so this is equal to a e to the power minus t by 2. Okay, and therefore the correct answer is option b. Okay, c to the power, c is the air constant here, minus t by 2, this is the answer. Now go to the next one. Question 21. Let y1 and y2 be two linearly independent solution of y double dashed plus sin x into y, this is equal to 0, 0 less x less 1, and gx equal to w of y1 y2 on x. Okay, so gx is the Wronskian, gx means w of Wronskian. Okay, a function of g. So be the Wronskian of y1 and y2, then which of the following option is true here. Okay, Now we first calculate Wronskian of x. This is equal to gx. This is equal to what? A into e to the power minus integration coefficient of first derivatives. Here first derivative is not present, that means 0 by 1 into dx. So this means 0 means e to the power 0 means 0, so simply a. Therefore Wronskian, that means gx is equal to simply a constant. Okay, and this implies g dash x, this is equal to 0. Okay, so for all x belongs to closed interval 0 1, since this is simply constant, therefore g dash x is also 0 for all x belongs to closed interval 0 1. Therefore here option A says that g dash x is greater than 0, but g dash x is equal to 0 simple. Though this is not correct. Less than 0 not correct. Vanish only 1 point, this is also not correct since this is a constant function, and this is correct since for all point of 0 and 1. Okay, this is the correct option. Now go to the next one. Let y1 x and y2 x form a fundamental set of solutions. This fundamental set of solutions means linearly independent solutions. Okay, and of the of this d2y dx2 plus px dy dx plus qx into y a less x less b, where px and qx are the real valued continuous functions on closed interval 0 1. If x0 and x1 with x0 less than x1 are two consecutive zeros of y1x in AB, then which of the following options is correct? Here the concept which is important is that between any two consecutive zeros of y1x, this is also or y2x, between any two consecutive zeros of y1x there exist one zero of the another one y2x if y1 and y2 are linearly independent solutions. Okay, so here it is given that x0 and x1 with x0 less than x1 two consecutive zeros of y1x, that means there exists a point, suppose x star, in between closed interval AB such that y2 at that point this is equal to 0. Okay, this is the result. Okay, so that means here option D says that first we discard the options y2 x0 equal to 0, but y2 dash x0 not equal to 0, but we also know that this is incorrect option since we know that y1 and y2 if they are linearly independent solution cannot have a common 0. Okay, cannot have a common 0, and it is given that y1 x0 this is equal to 0 since x0 and x1 are two consecutive zeros of x1 and y1 at x1 this is equal to also 0. Therefore these two are zeros of x1, oh sorry y1, therefore this is cannot be a zeros of y1 sorry y2. Okay, so this is incorrect option. y2 has no 0 in x0 x1, this is also incorrect from this result. 1 0 exists in between x0 and x2 of y2. Okay, and this is says that y2 y1 x is equal to x minus x0 square p0x, where p0x is a continuous on closed interval AB with p0 x0 is not equal to 0, but this is never true. If this is true, then y1x has two zeros at the point x0. Okay, since this is square term, that means if we put y1x equal to 0, then this gives x equal to x0 and x0, that means x0 is the point is a 0 of y1x of order 2, but this is not true. Okay, so therefore option A is true, and this is says that y1x is equal to x minus x0 into q0x, where q0x is the continuous on AB with q0 x0 equal to 0. This is we get from Taylor series expansion. Taylor series expansion of y1 at with respect to the point x0. Okay, this is we get. You can also check this. Okay, so here option A is correct one. Now go to the next one. Let consider the ODE u'(t) plus pt ut. So u'(t) plus pt into u'(t) plus qt into ut. This is equal to RT. So this is a non-homogeneous equation, but t belongs to closed interval 0 1. Then which one of the following p, q and r are defined on 0 1 and continuous functions, and two solutions u1 and u2 are of the ODE such that the Wronskian of u1 and u2. Here just two results are necessary. Okay, Wronskian is never vanish, either never vanish on 0 1 or vanish throughout 0 1. Okay, throughout 0 1. Now the given that if we go to the option A, then wt equal to 2t minus 1. Therefore for option A, okay, we discuss this for option A. So if w we calculate Wronskian at 0, Wronskian at 0, this is equal to minus 1, and Wronskian at 1, this is equal to what? 1. Therefore Wronskian at these 2 points is not vanish, but if we put the value t equal to half, which is belongs to closed interval 0 1, so w at half, which is equal to clearly 0. Therefore here this is not vanish, these 2 points. In these 2 points Wronskian is not vanish, but a point which belongs to this interval vanish the Wronskian at that point. Okay, that means this cannot be the Wronskian. Okay, correct one. Now if we go to the option B, then option B says that sine of, if we take wt, this is equal to sine 2 pi t. Now if we calculate the Wronskian at the point 0, this gives w0 equal to 0 and w at 1, this is also equal to 0. Okay, that means in this interval, in this 2 point Wronskian is 0. So if we that means this is the case throughout vanish. Okay, but if we take a point 1 by 4 which belongs to 0 1, okay, so w at 1 by 4, this is equal to sine of pi by 2, which is equal to 1, but Wronskian is not vanished at the point 1 by 4. Therefore this contradict the result that it is either vanished throughout the interval or not vanished throughout the interval. Okay, this contradict the fact, so this is not true. Now if we go to the next one option, if we take C option, Wronskian, this is equal to cos of 2 pi t. Okay, now if we calculate w at 0, this is equal to cos 0, that means 1, w1 cos 2 pi means 1, but if we take t equal to 1 by 4, that means w at 1 by 4, this is equal to cos of pi by 2, this is equal to 0. Therefore in these 2 point Wronskian is not vanished, but a point which is belongs to the interval 0 1, 1 by 4, which is belongs to 0 1, at that point Wronskian is vanished. Therefore this is cannot be the, this cannot be also the Wronskian. Therefore the correct Wronskian is wt, which is equal to 1. Okay, at any point in between 0 and 1, the value of the Wronskian is 1, which is never vanished. So this is the correct option. Now go to the next question. The next question says that let y1 and y2 form a fundamental set of solutions. That means y1 and y2 are Li solutions. Okay, are Li. That means Wronskian of y1 and y2 is never 0 for all AB. Okay, for all x belongs to AB. Okay, this is equal to Wronskian of x. W is a function of wx. Okay, now where this and x0 is a point in between open interval AB. Both y1 and y2 cannot have a local maximum. Here another result is necessary, which is that y1, if y1 and y2 are the linearly independent solutions or solutions of Wronskian, then y1x and y2x cannot have a local extrema. Okay, that means if y1 and y2 are two linearly independent solution, then they cannot have a local minimum or they cannot have a local maximum. Okay, so option A says that both y1x and y2x cannot have local maximum at x0. Okay, both y1 and y2 cannot have a local maximum at x0. Okay, so this is the correct statement. Okay,